On our map of 50 algorithms, algorithm 32 is XGBoost. It sits in the classification category, right next to random forest, though the two approach the same problem from opposite directions. We know that random forest works through bagging. It builds hundreds of decision trees independently and averages their votes to reduce the variance of the final prediction. Because these independent trees cannot communicate, they can't fix each other's blind spots. A shared mistake simply becomes a biased final average. To solve this, we can build the ensemble one tree at a time. In this sequence, every new tree is designed to fix the specific mistakes made by the models that came before it. Simply averaging a group of weak guessers is often insufficient for high-dimensional data. For the most complex problems, the model must evolve through a series of corrections. Jerome Friedman formalized the math behind this process in 2001. But the algorithm reached a broader audience in 2014 when Tianqi Chen released XGBoost, a C++ implementation optimized for speed and regularization. 6 weeks later, data scientists used XGBoost for the Higgs boson machine learning challenge. Physicists needed to identify faint subatomic signals hidden in Large Hadron Collider data. The challenge required separating genuine particle detections from overwhelming background noise. Chen's algorithm took the top spot on the leaderboard. Over the next 2 years, XGBoost became the most frequently used tool in winning Kaggle solutions. The algorithm became a standard for tabular data because it treats wrongness as the most useful information in the dataset. On the left, random forest uses parallel trees that don't see each other's mistakes. Gradient boosting uses a sequence where each tree targets what is still wrong. This sequential correction reduces bias. Notice the orange arrows passing the residual from tree to tree. A residual is the mathematical difference between the model's current prediction and the actual truth. When we add a new tree in XGBoost, it doesn't try to predict the original target. It is trained exclusively to predict the residual left behind by the previous tree. By dedicating every new component to the remaining error, the ensemble builds its accuracy one specific fix at a time. The loop starts with a baseline prediction across the entire dataset, called F0. This is usually just the mean of the labels. We calculate the error of that baseline, the negative gradient, and feed it forward as the target for the first decision tree. In this example, we are trying to predict a house price of $300. Our baseline starting guess is $200. That leaves a residual of $100. Tree 1 is now built to predict that $100 gap. We scale that tree's contribution by a learning rate. Here, it's 0.5. Instead of adding 100, we only add 50. This shrinkage prevents any single tree from dominating the model. Our new prediction is 250. This leaves a new residual of 50, which tree 2 now attempts to fix. The process halves the error again. Over several rounds, the prediction moves from 200 to 250 to 275 and converges at 300. This iterative reduction of error is the result of performing gradient descent within the function space. On its own, a single shallow decision tree is a weak predictor. It can only capture a small fraction of the patterns in the data. However, by organizing thousands of these trees in a sequence, we create a model that captures complex, nonlinear relationships with high precision. This precision requires careful tuning. If the learning rate is too high or the sequence is too long, the model will eventually begin to memorize the noise in the training set and overfit. XGBoost achieves its accuracy by breaking a difficult problem down into thousands of micro-corrections. This complex mathematical sequence is triggered by a surprisingly simple interface. Next, we will look at the single line of code that begins the entire boosting loop. Curious instructional tone. This iterative process is abstracted into standard lines of code. Understanding that math is only the first step. Deploying this algorithm safely requires knowing exactly how much computational weight it places on your system's resources. This equation represents time complexity for training XGBoost, multiplying k boosting rounds by d features and n samples. That n log n multiplier represents the heaviest computational drag, sorting through every feature value to pinpoint the absolute best split points for the trees. Then there is the spatial memory complexity. Your system must physically retain every node of all K trees in active memory simultaneously while it trains. Once training finishes, making predictions on new data is highly efficient. It is a fast mathematical traversal dropping down through those K-shallow trees. Unlike other algorithms, gradient boosting has no clean best-case scenario. The computational cost is a rigid contract that scales perfectly linearly with the width of your data and the number of rounds you run. To see exactly how this executes, we can pull the Chapter 7 Jupyter Notebook straight from the 50 Algorithms repository, https://github.com/cloudonum/50algorithms/main/chapter07/xgboost.ipynb. This code block displays the initialization of the algorithm. Look closely at the from XGBoost import XGB classifier statement. This Python class is actually a wrapper controlling a highly optimized, low-level C++ engine. That single import grants you access to enterprise-grade parallelization. It handles all of the heavy n-log-n sorting logic we just looked at, executing entirely under the hood without requiring manual memory management. Moving down to the instantiation line, nestimators 100 literally represents our K variable. It is the direct command telling the engine to sequentially construct exactly 100 shallow trees. Next to it, the learning rate 0.3 argument controls the shrinkage. It deliberately scales down the mathematical impact of each individual tree, ensuring no single iteration can dominate the ensemble. Setting max depth 6 enforces strict physical parameters on the algorithm. It guarantees every individual tree remains a weak learner, stunting its growth so it cannot over-memorize the training data. The .fit xtrain ytrain command serves as the ignition. Executing this single line triggers the entire 100-round loop, calculating gradients and second-order Hessians for every tree in the sequence. Manipulating these three specific parameters is the difference between blindly executing a downloaded script and intentionally engineering a predictive engine. This final section of the script handles the output generation. The .predict command sums the outputs of those 100 heavily penalized weak learners, thresholding their scores into a final binary classification. The resulting confusion matrix and accuracy metrics prove whether the ensemble successfully generalized its rules to new, unseen holdout data, aggregating hundreds of tiny, strictly controlled corrections. While XGBoost is unmatched in raw accuracy, knowing when its heavy computational complexity makes it the wrong tool for a production environment is the true mark of a senior engineer, and specifically its highly optimized implementation known as XGBoost. Its first major deployment advantage is purely practical. Real-world datasets are full of holes. XGBoost handles missing data values natively, out of the box, without requiring you to build complex pre-processing pipelines to fill in the blanks. It also cleanly processes both numeric values, like price or age, and categorical features, like zip codes or product types, side by side in the exact same pass. To survive in production, a model has to adapt to new data. XGBoost defends itself against memorizing the training data by utilizing built-in L1 and L2 regularization techniques, mathematically penalizing overly complex rules. And when your data grows, the algorithm scales right along with it. It is engineered to run effortlessly across distributed environments, like Apache Spark, AWS, and Google Cloud Platform. Because of this unique mix of high accuracy and extremely low pre-processing friction, XGBoost is the definitive first move for any data team facing a structured data problem. That reliability translates into a massive commercial footprint. In financial security, XGBoost is heavily utilized to detect fraudulent transactions and calculate real-time credit risk scores. In digital operations, it predicts churn, models click-through rates for digital advertising, and calculates pricing for insurance firms. It even powers the way we look for information online. Through an adaptation called Landlamart, gradient boosting provides the exact mechanism search engines use to rank your query results. Deep learning might generate the most press, but gradient boosting forms the invisible, decision-making backbone for the vast majority of global, data-driven commerce. This relentless, sequential bias reduction forces the model to continually attack its own weaknesses. That strict mechanical loop is why XGBoost consistently outperforms parallel ensembles. But that power comes with severe operational costs. Because the training must be sequential, it cannot be easily parallelized across rounds like a random forest. Every tree has to wait for the last one to finish, which drastically increases your training time. You also have to manage a massive hyperparameter payload to tune the model effectively. You are actively balancing constraints like the learning rate, maximum tree depth, the number of estimators, and regularization terms like gamma and lambda. If you get that balance wrong, the risk of overfitting is high, and the model will simply memorize your training data and fail immediately in production. You also lose interpretability. You are replacing a single mutable decision tree with an ensemble of 100 highly specific interacting trees, creating a functional black box where the exact logic is hidden from view. And finally, there is a hard territorial boundary. If you are dealing with unstructured data, like raw pixels, like text documents, or audio waveforms, XGBoost is the completely wrong tool for the job. The power of sequential error correction has a steep price tag: high tuning complexity, slow sequential processing time, and total opacity. This algorithm profile is sourced directly from 50 Algorithms Every Programmer Should Know by Imran Ahmad. You can find more details at neuralsca. Gradient boosting remains the ultimate strong learner, constructed painstakingly, one sequential fix at a time. But what if we leave behind tree-based, axis-aligned boxes entirely? Next time, we turn to pure geometry to draw the single widest margin street between two classes, with the support vector machine.